classification of the short-range entangled state. Or classification.
Thank you. I'll give a very informal talk because it's a work in progress. I think I have some good idea how to understand at least some topological phases of matter, or rather come up with a topological classifications of various phases. But there are many things that are not certain. So please don't trust me. And if you if you like something in my talk, please try to verify it. So. First, let me describe the big problem. I guess most people in this room are interested in understanding topological phenomena in quantum many-body systems at low temperature. So suppose we have a quantum many-body system in dimension n, and we want to distinguish trivial phases from non-trivial phases and assign topological invariance to non-trivial phases. What kind of non-trivial phases can be? What distinguishes a trivial phase from a non-trivial phase? There are two different things that I think are very different from each other. One thing is long-range entanglement or topological order. I'll not define it exactly. I'll rather define the absence of one. But informally, long-range entanglement means that local data, if we look at the system locally and do some local measurements, do not determine the global state. And that is easily understood in this example. Suppose we have a fractional quantum Hall state, say nu equals 1/3, the Laughlin state, and we make an annulus out of the electron liquid, and we can make local measurements in these disks that cover the annulus, any measurements we want. However, it's not possible to reconstruct the whole state of the annulus from the measurement outcomes, or not even measurement outcomes. If we just know the reduced density matrices on those disks, we don't know the global state yet, because in the middle there may be an anion with, the only way to detect this anion is to do some non-local measurement. For example, we can move another anion around this circle. This will be a non-local operator. So such things are interesting, but they are hard to understand, and I'll not touch them. I'll try to understand other phases, like integer quantum Hall effect, or topological insulators and superconductors. And they're interesting in a different way. They're interesting because the bulk is gapped, but the edge is gapless. So there is hope to achieve classification that would tell whether there is a gapless edge between two phases. Now we need to define short-range entanglement. And informally, short-range entanglement means that local data can be promoted to a global quantum state. A state can be reconstructed uniquely from the local data. Let's start with an example where we know for sure that it is possible. Even in that example, there is some little trick we have to learn. So I'll start with free fermions. And free fermion system is, for example, nu equals 1 quantum Hall effect, p plus ip, and so on. It can be a trivial phase also. In general, the Hamiltonian, the many-body Hamiltonian, is written in terms of Majoranas because I want to include superconducting systems where the charge is not conserved. Okay, and this is real skew-symmetric. And the matrix I times A is Hermitian and has eigenvalues like plus minus lambda j. They come in pairs. And we want to say that there is a spectral gap in this system, meaning that naively lambda j is greater than delta. Okay. Now, if it's an interesting system like the nu equals 1 quantum Hall effect or p plus ip, there is a gapless edge at the boundary, and we don't really expect that. If we consider the whole system, it will be gapless. So we need some notion of a local gap. And in this case, fortunately, it's pretty easy. First, we say that the matrix AJK is local. This means the following. There's indices J and K are associated to sites, say on the plane, on Rn in general, or in some disk in Rn. This matrix element vanishes if the distance between those sites is greater than some number. There is some maximal interaction range L. If Rj minus Rk is greater than L, then Ajk is 0. And let me call it an L local matrix. Instead of saying that lambda j is greater than delta, we can write a very similar condition. Lambda j squared is greater than delta squared, okay? And we can also write it this way. Minus I a squared as a matrix is greater than, greater or equal identity delta squared times identity. And using this condition, we can actually make sense of it. I mean, we can avoid this gapless mode at the boundary if we do the following trick. So, first, we may suppose that the spectrum is not only bounded from below, but also from above. And we may also assume, because spectrum is a soft thing, we can change the eigenvalues without changing the eigenvectors. And if we this is done by sacrificing locality to some degree. We can actually say that instead of this condition, we have lambda j squared minus 1 is smaller than little delta. And we can translate it in terms of matrices. We can say that I a squared minus identity. I am assuming that both numbers are approximately equal to 1. One is somewhat greater than 1. The other is somewhat less than 1. Then if we can write this and now it's actually a local condition. If we have this condition in each disk of sufficiently large radius, there will be the same condition in a bigger region, arbitrary big region. And the trick is that when we can say that it is a local condition on a region, we truncate the matrix, ignore the matrix elements outside that region. And the truncation can be done by multiplying by the projector. So the trick is that we multiply by this projector after taking the square of the matrix. And if we do it in this way, then there is a kind of equivalence between these two relations. If we have this relation globally, then we have that relation with the same delta locally. If we have this relation locally, then we have this relation globally with a slightly different delta. So the point is that we need to come up with a definition that is completely local. We don't want to talk about boundary because the boundary is going to be messy. And we need a purely local definition. Let's try to construct a purely local definition for many body systems.
Sorry, so for this case,
I'm a little confused. So you mean the first condition is enough for the boundary be local?
Yeah.
So that's a solution.
Oh, it's a local definition of a gap. So we may say that the Hamiltonian is locally gapped if this condition is true for every disk of some radius.
You mean it's equivalent to the
okay, let me make a precise statement. If this is true for all disks of radius r, then I a squared minus identity is smaller than delta prime times 1 plus O of that little l over r squared. So if this condition is true locally, then we have a similar condition globally with a slightly different bound.
This A is still the short range one.
Yeah, A is the short range. But the point of this discussion was how to define a local gap, because gap seems to be a global property.
I don't understand how this can hold if the gap is edge states.
Well, if you do it in a different order, if you replace A with pi d, A pi d, and then squared, it won't work.
Statement at the end, which is about the original A.
Yeah. So.
I mean that it's drawing on a big gap.
Which
is rather big.
Well, yeah.
It's the operator norm there.
Is that the norm, like second norm?
The original A, was a bit sloppy. The original A is kind of defined in an infinite system, but we can use a projector on an arbitrary big region that is covered by those little disks. So we may imagine that our A is defined on the whole plane or on a very big disk. Then we cut out a small disk using this projected pi, and then we can cover it by even smaller disks of radius r. And the statement is, if we do it for this relatively big disk, or if we do that for small disks, it doesn't matter.
Could there be some additional symmetry or something like that that would still leave you with gapless edge modes once you square it?
I don't know. I think the answer is no. I think it's a correct definition of a local gap. You first square and then truncate. And then you don't worry about the boundary.
Truncating, which is important, not squaring. Squaring doesn't change the spectrum. You only take gets you absolute values of the spectrum.
No, I'm worried about what's, well, if you, obviously, if you had truncated first and then squared, you're just moving the edge modes.
Mm-hmm. Yeah.
But the question is, is there some, well, go on, yeah.
Mm-hmm. Okay. Now, how do we define a notion of a short-range entangled state, not for free fermions, but in general? I will use the following fact about free fermions and try to generalize it. If we have a free fermionic system like a nu equals 1 quantum Hall effect, it can be cancelled by another fermionic system in this way. We take a nu equals 1 layer, a nu equals minus 1 layer, couple them, and this system adiabatically transforms to a product state. In terms of matrices A, we can say that there is one layer characterized by matrix A, another layer characterized by matrix minus A. And this overall Hamiltonian described by A and minus A can be adiabatically transformed to a trivial Hamiltonian, where each site on the top layer is coupled to a corresponding site on the bottom layer. And mathematically, it's done this way. We write matrix B like A minus A 0, 0. And it's a skew-symmetric matrix, like A. And we want to transform it continuously to this matrix 0, identity, minus identity, 0. It's a skew-symmetric matrix that describes the coupling between the layers. And this is called C. And the transformation is this. We write x of theta like cosine theta times b plus sine theta times c. And theta goes from 0 to pi over 2. And for the purpose of this discussion, let me forget about these boundary effects. Let's assume that these are just plain gapped matrices. The point is that these two matrices anti-commute with each other. And when we consider the matrix x squared, since B and C anti-commute, it will be cosine squared B squared plus sine squared C squared. And B squared is greater than a constant. Every eigenvalue is greater than some constant. And same is true for C squared. And all the way along this path, the matrix remains gapped. I guess it was first observed by Matt Hastings, but it's a really important property. We can adiabatically transform from two layers to a trivial system. There is some consolation property. And I'll use this consolation property as part of my definition of a short-range entangled state. The previous discussion was in terms of Hamiltonians. So there is some matrix. Its ground state is uniquely defined by the Hamiltonian. It's easy to compute for free fermions. And we should be more interested in the ground state itself than the Hamiltonian for various reasons. First, the ground state is more fundamental physically. And second, more importantly, if we fix the ground state and consider different Hamiltonians with the same ground state, at least we can focus on so-called unfrustrated Hamiltonians. Then the set of Hamiltonians is contractible for the same ground state. And if we want to do a homotopy classification, those Hamiltonians can be ignored, and we can focus on the ground state itself. So one idea is that a short-range entangled state, it's an idea for the definition. A short-range entangled state has a cancellation property like free fermion systems. And yeah.
The statement that set of Hamiltonians is contractible for a given ground state.
Yeah.
For free fermions, for short-range entangled systems, for.
Okay. We can consider gapped Hamiltonians. A gapped Hamiltonian can always be replaced by a so-called unfrustrated Hamiltonian. An unfrustrated Hamiltonian is one where each term annihilates the ground state individually, and the terms are positive semi-definite. And those terms are local, but they have some exponential tails. They are not strictly local. if you want to cut those tails, then this property will be approximate. The point is, when we have two such Hamiltonians, we can continuously interpolate between them, preserving all the important properties. So such Hamiltonians for a given ground state form a convex set. It's unfrustrated Hamiltonians. Of course, if you just think about arbitrary Hamiltonians, it's not so clear, because if you interpolate between two Hamiltonians, the gap might vanish. It's not obvious that it doesn't vanish.
So your definition of unfrustrated also includes a gap.
Yeah.
That's a special.
Yeah, but right. But I'm not talking about that. I'm talking about the short-range entangled states, because that notion is more general for gap systems. I wrote about that in my honeycomb lattice paper, and Matt Hastings wrote a paper about that, about unfrustrated Hamiltonians. But I don't think that anybody proved it explicitly that the set is convex. So
Here's the convex. You have a bunch of terms that all annihilate the same ground state. You can certainly take linear combinations and they're still annihilated.
yeah. The only problem with convexity is the gap, the possibility of vanishing gap, I think. Now, let's first try a tentative definition like this. We need to incorporate two things. One is that our definition must be local. We don't want to ever talk about a vector in a Hilbert space, in the global Hilbert space, because the boundary conditions are unknown and they're nasty. So we want to be able to define it in purely local terms. And the other property I'll use is that cancellation. So one idea would be to define a quantum state as a linear functional. Usually a quantum state is a linear functional on apparatus. The density matrix is a positive functional on the operator algebra. But let's consider linear functionals that are only defined on local apparatus. We consider actually all disks of radius r, and consider define psi by the expectation values like this. It's x psi where x is contained in a disk of radius r. Radius L, for example. Maybe R. I want to keep the analogy with the previous case. Let it be R. This set of data is equivalent to specifying the reduced density matrices rho taken the partial trace over the complement if we have some disk D, we trace the complement. Let me use this notation. We trace the complement, and we may call it rho D. And suppose we have density matrices for each disk of radius r, and those density matrices are consistent, meaning that if we take the overlap, you reduce both density matrices to the intersection, they're the same. However, this local consistency does not guarantee that such rho exists globally or that it is unique. And the uniqueness problem we have seen previously with this annulus. So we need an additional condition. And that condition will be that those density matrices can be generated locally by a quantum circuit from a product state. So going back to this example, this transformation was an adiabatic transformation of Hamiltonians. But it can also be viewed as an evolution of the quantum state. And it's a continuous adiabatic evolution. It can be discretized in small steps and transformed into a quantum circuit to some approximation. So in this example, we already have a quantum circuit that takes the ground state of this Hamiltonian to the ground state of that Hamiltonian. And we want to have a general notion of such a transformation. I'll just use a circuit for the general notion. So the idea is that we have actually consistent a set of density matrices for disks of radius r, and for each such disk, let me use a one-dimensional picture. The disk will be just an interval of length r. There will be a quantum circuit that is defined on a slightly bigger interval, r prime, and I just want to give you the idea. I'll not specify the detailed relation between these two. But the idea is this. This quantum circuit consists of local gates, and the vertical direction is time. So let me just draw this circuit. And it starts with all zeros. And then those gates are applied. And this circuit has a small depth, sufficiently small depth. And this circuit is required to produce a quantum state in this slightly bigger region. And you see that the circuit also produces some garbage because those qubits are just lost. Nevertheless, it's required to produce the correct state in this region. But this would be an example of a trivial state. if psi itself can be produced by a circuit. Let me call this circuit U, and we write that psi is equal to U times 0. And I'm sloppy writing that. I'm writing as if psi were a quantum state, but it isn't. It's just defined by some data.
Psi is the same as rho. Basically.
Yeah. I want to think of it as a quantum state. Yeah, it's the same as rho. But this will be a trivial state. What we actually need, we need the existence of a circuit that would produce psi along with some other state. So we actually say that this is trivial. And the non-trivial one will be psi tensor eta equals U times 0. And everything is very sloppy because there is no vector psi. There is only quantum state psi defined as a functional. But the idea is this. We can simultaneously produce the desired state and some garbage so that together they're equivalent to a product state by that circuit.
Circuits were designed to produce the state rho sub d for each disk radius.
Yeah. So we can say psi d. Yeah, that's right. Now, the key thing is that if we have...
Not always given a density matrix rho d, it's got some finite rank. Can't you always produce it by a circuit, or there's a limit on the size of the circuit?
You'll see from the following discussion why the depth is important and what the limit is. The idea is that there is a light cone, and there is another light cone. And we can iterate it. And it turns out that as we start gluing different pitches, we lose part of the space. It's like we have pieces of paper with some fringes on the boundary. We cut them, try to glue, but as we glue, we have to cut more and so on. And the idea is that those disks should be sufficiently large so that the patching is possible. I'll describe the patching, and you'll see what actually happens during the patching. Suppose we have two regions. One region on which such a circuit exists, and another region. And let me make them overlap by quite a bit. So these are two regions. On one region, there will be a circuit that produces this state, circuit U, and I'll draw it in this way. So it starts with zeros on the bottom, and the qubits on the edge are lost. And there is another circuit that can do the same for this region. And we want to construct a new circuit that would produce the same state, or a state with the same local properties, because we don't have a state really, we have some local properties of that state. But we want to do it in a bigger region. We want to glue them. So the gluing works like this. This is U. And we run the circuit that produces V. Recall that V is defined on a bigger region. Sorry, not on a bigger, on a different region. We run the circuit backward. So now V minus 1. Okay. Well, we cannot really do that because we don't have these qubits. So what we do is this. This is part of circuit V minus 1. And it also generates some garbage. Then on the top, we have 0, 0, 0. And here we actually have another set of qubits that we keep. And after that, we run V in the forward direction. No, on the right we cannot do that. At the right we have cut in this way. On the bottom, this V should be given some zeros, and those qubits are fed back. And so this way we have patched the two things.
Sorry, what's the consequence?
No.
The consequence is this. We can also keep track of these qubits. And we have generated a consistent state on a larger region.
Which has which reduced to
The same dimension we had before.
It's roughly the union of the original two regions. However, we had to cut from various sides. For example, if we want to glue two states that are produced by circuits in regions A and B, we have to cut a little bit from A and a little bit from B, and we will erase this space. So eventually we'll generate a circuit that is defined on on this thing. So notice that the original disks A and B were larger. So we had to cut while gluing. So in this definition that we have cyaneta is important in this construction because notice that we have also generated some garbage in the middle. Let's call it eta. Of course, it's important to prove that eta and psi are not entangled, that it is indeed a product state, but that can be verified. It can be verified that this psi cannot be entangled with that state eta, and basically, if we look where these qubits come from, and those qubits come from, and we need to keep track the causal origin of this whole garbage state, and make sure that it doesn't overlap with the causal origin from the other side. Actually,
true if it's big enough.
yeah, it's true if it's big enough.
So
Where
is the region that you
cut out like AB, and then you have to reduce a little at the corner. In this picture, where is that region?
In this picture, so suppose this is A, then we cut on this side, and then we patch by adding zeros and running this circuit V. However, in two dimensions, we cannot completely restore, because first we have region A, we cut it to a smaller region. We don't have to cut all the way around, it's just here. Then we replace, we put some zeros on this place where the cut was. Then we draw this region corresponding to B, and we run the circuit, but we cannot fully regain what we cut. So there will be some region that is lost at the corners. Because well, you need to draw a two-dimensional picture to see how it happens.
General picture is that if I know the circle to generate the row A, and then the circle to generate row B, then I can construct the circle which generates the row A plus B, subtracting some small region.
Yeah.
And then you can generate the whole system.
Yeah, exactly. Okay. Now let me talk about properties of such states. As I say, I'm not trying to be rigorous. It's a very informal discussion. Nevertheless, I think I understand some properties, and although I don't completely verified how they follow from the definition. It seems that they follow, but there may be some subtleties. For example, in this circuit, we need to use some notion of precision, because we do not expect to generate the state exactly, only to some precision. But I think it's a minor issue. Suppose we have a disk Dn, in dimension n, and this is a big disk. Those local patches are very small compared to it. And we define spaces Bn and Fn. Bn is the space of nice Hamiltonians, short-range, or nice quantum states, sorry, in this disk. And F for bosons, and Fn is the same for fermions. Bosons means that on the lattice there are spins, and fermions there are itinerant fermions. They can hop between sites. And these are two different questions. The questions are to find the spaces of nice quantum states and find their connected components. The connected components would be the faces, but actually it's interesting to look at the whole set as a topological space. N is the dimension. It can be 2, 3, so spatial dimension. And if there is a symmetry, one can also consider faces of matter with symmetries. And the condition is that the density matrices commute with the symmetry generators, and all the gates in the circuits used also commute with the symmetry generators. And this G acts as an internal symmetry. It acts on each side independently. Internal symmetry. I wish to claim that if we find a solution to the first problem, then the second one will come for free, almost, because it requires solving some topological problems. But we don't have to talk about quantum states anymore, just do some topology. What do we know about Bn and Fn? First, let's define Fn-free. The space of free fermionic states, or free fermionic Hamiltonians. What is it topologically? Fn-free is the space of locally gapped matrices A. Here is an interesting fact. If we write the Hamiltonian in this form, it's a discrete Hamiltonian on lattice. And it's not even translation invariant, more or less arbitrary. We can transform it adiabatically to a continuous Hamiltonian. Continuous actually means discretized, but on a much finer lattice. It's integral of eta transposed mu, gamma mu, d mu, plus m of x, and also this imaginary unit. And this is a column vector of Majorana fields. It's eta 1 of x, eta k of x. And this is a mass term. And furthermore, there are certain relations between those things. The relations are the gamma matrices are real symmetric matrices, and they have this anti-commutation relation. M is a real anti-symmetric matrices, and it squares to -1, and -1 because we want it to be gapped, and M squared equals any gapped matrix can be continuously deformed to a matrix whose score is +1 or -1, depending on the symmetry. And finally, gamma mu M is 0. So an arbitrary lattice Hamiltonian can be transformed to this Dirac type Hamiltonian with varying mass term in space.
So in what sense can it be transformed? If you're subdividing the lattice, you introduce a lot more degrees of freedom.
Yeah, it is allowed to add degrees of freedom that are initially in a trivial state, and then we can entangle them. And the rough idea how to do this transformation, it's very, very quick.
If the initial Hamiltonian was translation invariant, is M of X also translation invariant?
You mean discrete translation invariant? Yeah. It will be. So the idea is this. Let's start with the lattice Hamiltonian on a chain. And this lattice is just on X, but I'll draw it on a diagonal just to make things easy to visualize. Y is basically a copy of X. So we have a chain along the diagonal, and these sides are coupled to each other. At the first step, we replace each side by a Jackie-Fraby soliton. Keeping the interaction. So the idea is that we want a localized state become an extended state. And one naive idea would be to put a particle in a potential well and let it sit in the ground state of a harmonic oscillator. But that doesn't actually work because we want it to extend to sufficiently large size without diminishing the gap. And the harmonic oscillator, as the size gets big, then the gap becomes small. So it doesn't work. But the following thing works. We can replace each side by a Jackie-Fraby soliton. And these solitons will be coupled diagonally. And step 2, we adiabatically transform the diagonal coupling to vertical coupling. Now, all the matrix elements in this system are vertical except the kinetic energy of the Jackie-Fraby solitons. And you can check that the metric, the Hamiltonian will be of this form. But what is the dimension of M of X? The dimension of M of X is related to the number of sites each particular site interacts with in the original system. So if it interacts with 10 neighbors, then we have to use 10 by 10 matrices. Actually, we need to multiply by a factor 2 to the n. There is an additional factor because we need to construct the gamma matrices. That gives 2 to the n. But it's still a finite size of those matrices. So if we focus on this form of the Hamiltonian, and we're only interested in classification of faces in a disk, not on a torus, for example, just on a disk, then it's enough to consider the mass term at the center of the disk, at a single point, for the classification purposes. And so the problem is reduced to classifying matrices M that anti-commute with the gammas. So F and free and speaking abstractly, we may say that the gammas define a representation of a Clifford algebra with n positive generators. And we want to extend this representation by adding m as a negative generator, because the gammas together with m form a bigger Clifford algebra. So M free is extensions of representation of Clifford 0 n to a representation Clifford 1 n. And a very good reference is Karoubi's book on K-theory. The structure is exactly the definition. I mean, connected components of N free are related to K groups of the disk relative to the boundary. And those K groups are exactly defined using this representations of Clifford algebra. And if we are not interested in connected components, if we are interested in the whole space, then let me just write down what this N free is for different N. What is F0 free? That should be easy, because we're talking about skew-symmetric matrices with a gap, and we just say A squared equals minus I, no locality condition, and no Clifford algebras. And the same can be done for M instead of A. We can just say that this M and that A in 0 dimensions are the same, because there are no derivatives. And M free is the space of such matrices, which is O of 2n, n is the number of indices here, divided by U of n. And we can take the limit of n going to infinity, because we don't restrict ourselves to any particular number of sites or number of modes for this.
But he used a different method.
Oh, yeah, thank you, yeah. K. Yeah, I used K there. Yeah, it's the same K. It should be 2K, actually. Right. And this should be the limit over K. And we can just say that it's O over U. And let me write a table it will be N, F, and free, and okay, let me just consider the connected components. These are connected components of this topological space, which is the same as faces of free fermion systems. And for dimension 0, the space itself is O divided by U, and the set of connected components is Z2, and the invariant is the Pfaffian, because we're talking about this skew-symmetric matrix M. It has Pfaffian equal to plus or minus 1, and that's why Z2 here. 1, it's O, and it's also Z2, because an orthogonal matrix has determinant plus minus 1, and 2, it will be this space, BO cross Z, and I should define BO. It's the limit of say O of 2k. I can even use 2 indices k plus m divided by OK cross OM. And k and m go into infinity. And faces are defined by Z. Now, physically, what are the trivial and non-trivial faces in each case? In the first case, the Pfaffian of matrix M defines the number of fermions in the ground state, whether it's even or odd. In the second case, the non-trivial faces in might run a chain, and this invariant tells whether there is a dangling Majorana mode if we cut the chain or not. And here it's the generator is P plus IP superconductor. This sequence continues. It corresponds to the real K-theory. Those states form the spectrum of real K-theory, KO. I mentioned, actually, I don't know how much time I have.
So, how long do you plan to?
Well, I can continue, but it depends on the audience whether people want to continue or not.
But at least want to hear about the interaction part. So maybe
Yeah, sure.
about another half an hour.
Mm-hmm. Okay. Mm-hmm. Mm-hmm. Okay. So I mentioned a word spectrum. There's spaces F3 and actually F and B interacting form a so-called omega spectrum. The condition is that
Sorry, let me ask you one question. The statement that you were making about this replacement, it tells you that the bulk gap is retained in this US process, I guess that's the thing, right?
the bulk gap is
retained. So you're thinking about a system that is either without edge or in this process of discretization that you...
Oh, yeah. The bulk gap is retained, yes, so that's right.
It's either defining the bulk gap in the way that you did, if you consider a system with an edge, or a system without edges, right, or an infinite system, something like that.
Well, I consider a system, but with an unspecified boundary, and I don't care what happens at the boundary. Because we have a good notion of a local gap, we only care about the local gap.
Okay.
An omega spectrum means that Fn is homotopy equivalent to omega, the loop space of Fn plus 1. That is true for F free, and also for bosons. Bn is equivalent to omega of Bn plus 1.
What's omega?
Omega is the loop space. The loop space. And before explaining this property, maybe we should discuss B0 and F0 in the interacting case. B0 is actually CP infinity because what is an interacting system in 0 dimensions? It's just a quantum state with no locality conditions. And it's defined up to phase, and its dimension is can be arbitrarily big. That's why CP infinity. It's just a limit of, you can say, CPN for very large, CPK for very large K. But let me return to infinity. And F0 is CP infinity union another CP infinity. Because the system can have states with an even number of fermions and an odd number of fermions. That's why it has two pieces. Now,
Are you going to explain why these two equations are?
yes. Let's focus on this equation. B1 is equivalent to omega of B0. And let's further focus. Oh, yeah, sorry. Yeah, thank you. And let's further focus on a map from B0 to B1. So this map should take a zero-dimensional system and produce a one-primed family of one-dimensional systems. So it will be a chain system, a quantum state on a chain that depends on adiabatic parameter in the loop space. And this chain state will begin with all zeros, the product state, and will end at the same state, but in the middle it will be non-trivial. So it will be a continuous process, starting and ending at the product state. Now, let me mention something about B0. It's CP infinity, and it's a connected space, so we don't have any non-trivial phases. We can move from any state to any other state. However, if we have families, we consider families of states, there may be non-trivial families. For example, if we consider a spin that is polarized in a given direction, spin 1/2. It's a U1 bundle over the sphere, and such a bundle for the spin polarized by a magnetic field has Chern number equal to +1 or -1. So this is an example of a non-trivial family. And this is a one-dimensional, two-parameter family in B0. By doing this transformation, we are going to produce a three-parameter family of chain Hamiltonians. So to make this picture non-trivial, we need at least three parameters. But the construction is canonical, so we can add those parameters later. We can just talk about the state itself. An element in B0 is the parameter. So the parameter space will be just CP infinity. So let's start with such a state psi. And let's draw a picture. This will be x, and this will be t, the adiabatic parameter. And we begin with zeros. Product state. And the final state, it should also be zeros. And this happens at t equals 0. The zeros should return at t equals 1. And in the middle, something will happen. At t equals 1/2, there'll be alternating state psi and eta. Recall that we cannot generally construct psi, but we can construct psi and eta simultaneously. And they will repeat this way.
So your psi stands for what? 1D state or 0D state?
Psi and B0, zero-dimensional state. And this psi will become a family of 1D states. So in the middle, we want this thing, and it's constructed like this. First, we apply our circuit that generates psi and eta out of zeros. And we do it on all those pairs. And then we annihilate eta and psi. And in the end, we get almost all zeros, psi on the left and eta on the right. But the boundary conditions are not important. All the definitions are set up that we don't care about the boundary. However, physically, it means that this state psi was pushed through this one-dimensional chain. And it's very similar to a charge pumping phenomenon. So the idea is that for any topological invariant, in this case zero-dimensional, there is a pumping phenomenon in dimension 1. And for any n-dimensional topological invariant, there is a pumping phenomenon in dimension n+1. Of course, you may ask, to specify this circuit, you need more information. You need the actual circuit. We don't have a canonical circuit defined by psi. But it turns out if we fix psi and consider all circuits that generate psi together with in some other state, for a given psi, this space is contractible. Sorry, not circuits, adiabatic processes, continuous processes. For a given psi, this space is contractible. If we fix psi and consider all adiabatic processes that generate psi together with some other state, the space of such processes is contractible. And so the only non-trivial topology involved is about psi, not eta, and not the concrete circuit. I wish I could say that eta is equal to psi bar, the complex conjugate of psi, all the amplitudes complex conjugated. Unfortunately, I cannot prove that. And
you cannot prove that you can make that choice.
Yeah, I cannot prove that I can make this choice. And it's a very desirable thing to prove.
But you mean like
If I take eta equals psi bar, I cannot show that psi and psi bar together can be equal to 1?
Well, I cannot show that, but it doesn't mean it's not true. Yeah.
So I don't understand the requirement here because psi is a zero-dimensional state. So
Yeah.
psi, so eta is another zero-dimensional state. So in zero dimension, I don't have a requirement of locality, so I can.
Oh, sorry. No. Yeah, right. You're absolutely right. In 0 dimensions, it's true. In 0 dimensions. Yeah, for high dimensions. For high dimensions.
So basically, this construction, I can understand it as like any site Hamiltonian can realize it on the soliton of 1D Hamiltonian.
Yeah, exactly.
So soliton is like between one dimerization and the other dimerization. So
Yeah, exactly. And this is exactly the inverse map. If we have a family of systems, we make a soliton, which is a zero-dimensional system. Okay. So this is quite general, and it implies that pi n plus s of fn is equal to pi s sorry, I should say this thing does not depend on n. It only depends on s. Because if we increase n and simultaneously add one more degree of looping, we go back. So this sorry, I made the jump. This condition implies that pi k of bn is equal to pi k plus 1 of bn plus 1. And then we can say that this thing only depends on s but not on n.
As long as s is non-negative.
Yeah. Well, s can actually be negative. It can be. Well, it depends. It's true in a range of n. Yeah. Right. Yeah. So since we have these very general properties, we can try to de-loop B0, because we know B0 and F0. It should be equal to the loop space of B1, and we can just try to solve this equation. Now in Bn, try to find Bn plus 1 according to this equation. The solution is not unique. However, in lower dimensions, it's easy. And it's known, for example, that B1 is the Ellenberg-MacLane space KZ3. And this should be compared with this formula, KZ2. The general definition of K H M. The definition is this: H is an abelian group, M is an integer, and pi k of that is equal to H if k is M, 0 otherwise. So this space has a non-trivial third homotopy group, and that space has non-trivial second homotopy group. And this pair satisfies the equation. It satisfies this equation, and it satisfies that equation also. And it's the actual answer, because one-dimensional states can be classified using the matrix product approximation. And in high dimensions, it becomes trickier. B2 is expected to be equal to KZ4 cross Z. So the fourth homotopy group is non-trivial, but there are also non-trivial connected components, non-trivial faces, and those faces have to do with the chiral central charge. If we consider a 2D system of bosons or fermions, at the edge there are gapless modes, and they can be characterized using the conformal assumption, using the assumption that the H is described by a CFT. They are characterized by C minus C bar, this number. And it has physical meaning. It defines the energy current on the edge if the edge is at finite temperature. The bulk has very large gap, so it cannot be, or we don't consider it at finite temperature, 0 temperature. But the edge is at finite temperature, and the energy current is I pi over 12. It's a result from CFT, C minus times T squared. The energy current on the edge. And from this formula, it's clear that C minus is a bulk property, because all the energy goes along the edge and cannot flow into the bulk. If something changes on the edge along the way, the energy current should not change.
So this D, but
This is not what I can read from the equation, right?
No, this Z is not defined by the equation, because when we loop, when we consider loops in one phase, we pick a base point, and the base point corresponds to c minus equal to 0, and we only loop within that phase, so we don't see the other phase.
So I should understand that in the equation, it's not the right side is not all the loops. It's the loops.
Yeah. These are base pointed loops.
And the non-trivial ones are just not entering the equation. So in any dimension, I'm not directly telling anything about the non-trivial.
Right. We don't see the non-trivial components. And if there is a delooping process with non-trivial components, we can just kill them.
So I mean, if I don't have this physical picture of central charge, is there some other equation which determines whether I have this other?
No, I don't know of such an equation. That would be nice.
So that means I also don't know when I go to higher dimension whether there is new things like.
Right.
So are you saying the chiral central charge is the only invariant needed for these phases in 2 dimensions?
I believe so. I cannot prove that.
And also, are you saying it's an integer?
It's a multiple of 8. For bosons, 8 times m in fermions and this condition comes from the requirement that there are no anyons in the bulk, and the CFT should have just one sector, no non-trivial sectors.
So you're still talking about these short range?
Yeah, short range phases.
But was that used somewhere in this analysis? I guess you're...
I can
use this.
We can cancel cyaneta. This is the key property. So what else can we say? We can relate F and F-free. There is some general relation, and in low dimensions we can actually reconstruct F from F-free up to dimension 1 for sure, and modulo this conjecture, modulo the conjecture that this is the only invariant in dimension 2. So let me just say what I could try to explain. One thing is the relation between phases with and without symmetry. And the claim is, if we know there are spaces, either Bn or Fn, we can also classify phases with an internal symmetry, more or less automatically. So this is one thing. And another thing, it's very speculative, about the gravitational anomaly. Because in field theory, this central charge is related to the gravitational anomaly. And people have argued that for condensed matter systems, for lattice systems, one can also define gravitational anomaly. To me, it seems that there is a problem defining gravitational anomaly. It may or may not exist. I mean, it may or may not be defined. Because to define a gravitational anomaly, one needs to put a system on a manifold. And from this general nonsense, I mean, from this condition that it is an omega spectrum, we can only define a procedure of extending the system from a disk to a normally framed manifold. There is a well-defined procedure to put a system on a normally framed manifold. And you can see how a system on a disk can be put on a sphere. A sphere is embedded in 3D, and it's normally framed. There is a perpendicular direction. And just to give an example, we have a state psi on a disk, and I draw it this way. And there is a state eta also on a disk, but I bend it the other way. And here, these are two-dimensional states in principle. There is a circle there. And here we can apply this transformation that transforms cyaneta together into the trivial state, but we apply it to different degrees at different places. Far away, it will be complete, so it will be 0, and here it will be partial. So we can glue these two disks with cyan eta to make a sphere. And there is actually a general procedure using this omega spectrum condition to put a system on any normally framed manifold. To put a system on a general manifold, we need more structure. And I believe that the correct structure is that we need, if we want to put fermions on a spin manifold, free fermions can be put on a spin manifold. If we want to put interacting fermions on a spin manifold, we need that the spectrum is a module over the M spin spectrum, the spectrum of the spin cobordism theory. That would be a natural homotopy theoretic formulation of putting a system on a manifold. So I don't see how to construct this structure.
The manifold you're talking about is just space, not space-time.
It can be space-time. So if we want to define a partition function in space-time, we can define it as a loop in the, say, just a second. Suppose we have a two-dimensional quantum system. A two-dimensional system is equivalent to a loop in the space of three-dimensional systems. A loop in the space of n plus 1 dimensional systems can be viewed as a partition function, a special kind of partition function in dimension n plus 1.
Can be assigned a partition function.
It can be assigned partition. Yeah, thank you. Yeah, it can be assigned a partition function. Actually, it's an interesting question how to assign a partition function. I don't know how to assign, how to do it exactly. N plus 2 will be a partition function. Sorry, it will be an integer invariant. So okay. Let me just talk about this other thing, relation to symmetries, how we get to symmetric faces from arbitrary faces. the claim is that if we want to classify states with symmetry, internal symmetry G, we need to consider maps from the classifying space BG to Bn or Fn, say Fn. This is the simplest case when there is no twist. There is a twisted case which is more complicated. But both cases can be explained in the following way. We have symmetry group G acting on Fn. So G cross Fn goes to Fn. This is the symmetry action. And we want a fixed point of this symmetry action. A fixed point will be a symmetric phase. So a quantum state psi is in F and G if G of psi is equal to psi for all G in the group. Now there is a weaker notion than a fixed point. It's an opto-homotopy fixed point. Let me describe it vaguely. Suppose we have some state psi that is not invariant under some group element G. So psi and G of psi are different. However, it may be possible to connect them by a path. So if we connect them by a path, in the first approximation, it's like a fixed point from the topological point of view. But there is a potential problem if we apply the symmetry to this path. And for simplicity, let's assume that G is Z2. If we apply the symmetry to this path P, we get another path, and it's G of P. In principle, it's a different path. And if we can connect them by a disk, then it's good. If we cannot, it doesn't look like a fixed point. So an opto-homotopy fixed point occurs in a situation when we can continue this process indefinitely. We can apply the symmetry to this disk, obtain a sphere, and fill the interior of this sphere and continue. So mathematically, it means the following. It means that there is an equivariant map, or G map, G equivariant map, G map F from this thing called EG to Fn. What is EG? EG is defined up to homotopy by two conditions. If EG is a space on which the group acts, and G acts on EG freely. Freely means without fixed point. this is condition 1, and condition 2, EG is contractible. So, this condition is a definition of an up to homotopy fixed point. F is called
You mean F represents a class of Hamiltonians?
F represents a family, a class of Hamiltonians, yes.
Which are all
symmetric up to homotopy.
Right. So up to homotopy means that this family is parameterized by EG that is a contractible space. It's very simple. It's not a point. If we replace EG with a point in this definition, then a G map in general is a map that commutes with the action of G. A map from a point to Fn that commutes with the action of G is a fixed point. So this is just a slight relaxation of the fixed point condition.
So somehow, you're.
I mean, is there a condition like when I act G on EG, then then the image of this map is acted by is the same as the action of G on the Fn? I mean, there is an action of G on BG, and there is an action of G on Fn.
Yes.
And then basically these two commute.
Yeah.
With this map.
Exactly. If we apply this map first and then act on Fn, it's the same as acting here and applying the map.
So that's not in these two conditions. We need a third condition.
No. It's the definition of EG, and here I use this term G map. A G map is a map that commutes with the action of G.
Okay.
It's called G equivariant. It's just for brevity. It's called G map.
Is it true that if you find such a fixed point up to homotopy, then it can be directly connected to a real fixed point?
In general, it's not true. In this case, for quantum systems, interacting quantum systems specifically, in this case, interacting beta, given an up to homotopy fixed point, we can connect it to a true fixed point. And here is why. We can construct a new system which will include a Bose field. And the Bose field will take values in EG. Actually, we can approximate EG by a smaller thing. EG, in principle, is very big, like an infinitely dimensional sphere. But we can approximate it by a finite sphere. So it will take values in EG, and it will be a kind of sigma model. It's a Bose field that is coupled to the fermions. And the image of any point here in Fn is not a fixed point. However, the whole ensemble will be a fixed point. And we can show, at least using a particular model, there is a particular model that takes this map as input and produces a quantum Hamiltonian whose ground state will be an equal superposition of all field configurations over EG. And each field configuration will be accompanied by the corresponding fermion configuration. And they will change into each other adiabatically, and this process will have a gap. So the conclusion is that any homotopy fixed point corresponds to an actual fixed point, and this relation is one-to-one.
So the classification with
Symmetry T is given by pi 0 of these maps.
Yes, yes, exactly. Yeah, I think that's it.
more questions.
We actually had a lot of discussion already, so thanks, Alexei.